Hello, everyone. Welcome, welcome. People are trickling in. All right. Hello, everyone, and welcome to the University's Research Association URA National Lab Seminar Series. We're delighted to have you with us today. Headquartered in Washington, D.C., URA is a nonprofit consortium of over 90 leading research universities across the US, the UK, and Italy. Our mission is to accelerate scientific discovery by strengthening the exchange of expertise between academia and our national laboratories. In this capacity, URA serves as the parent organization managing Fermilab and provides key support to Sandia National Laboratories. The goal of this seminar series is to broaden your understanding of the range of career paths available with a STEM degree beyond traditional academia, and to learn more about the work being done across the 17 U.S. Department of Energy national laboratories. Please use the Q&A feature at the bottom of your screen to ask questions for the Q&A session, which will happen at the end of the presentation. We're pleased to welcome our speaker today, Dr. Samantha Kruse. Dr. Samantha Kruse is a postdoctoral appointee in the Analytical Science and Corrosion Department at Sandia National Laboratories. She earned her Bachelor's of Science in Chemistry from Northern Arizona University and her PhD in Chemistry from the University of California, San Diego, where she studied the chemical transformations of sea spray aerosol in the atmosphere. At Sandia, Dr. Kruse is focused on developing innovative analytical techniques to tackle emerging challenges related to national security. She's also the 2026 National Lab Research Slam winner in the Advanced Materials category. Welcome, Samantha. The floor is yours.
Thank you for the lovely introduction, Natasha. Let me go ahead and share my screen. Alrighty, can you see that?
It, yes, has loaded. We can see it.
Okay, perfect. Alrighty, thank you everyone for attending this seminar today. I'm really excited to share my experience working at Sandia as well as just kind of my career path and how I got to the job that I have today. So just a little, well, fans. There we go. Just to kind of go over kind of how the talk is structured. I'm going to go through step by step, kind of every stage of my career that I've had. So I'll start out explaining some of the research that I did as an undergrad at Northern Arizona University. And then I'll spend a bit of time talking about what I did for my PhD research and how that motivated some of the projects that I've been working on at Sandia National Laboratories. At the end, I'll also give a brief overview into the labs and kind of talk about some pros and cons for working here, as well as some opportunities for students that I'm aware of here at Sandia. So to start off, I grew up in Arizona. If anyone is familiar with the East Valley area, I grew up specifically in Gilbert, Arizona. But if you aren't familiar, it's basically just a suburb within Phoenix. Phoenix is a huge city. And growing up in Arizona, we would have seasonal monsoons, which, if you are familiar with, you probably understand that they are so crazy. They're these like massive rainstorms with tons of thunder and lightning. And so I always just really enjoyed sitting outside and looking up at the sky and watching these storms come in. And I also really enjoyed my science classes growing up. That probably isn't too much of a surprise to anyone, right? You kind of have to like science to decide you want to go into science as a career. But at the time growing up, I was definitely very focused on having what I would consider an impressive career. So I thought, well, I like science. So what if I was a neurosurgeon? Which is really funny to look back on now. But I was so set on being a neurosurgeon and going to med school and all of that. You'll understand in a second why I'm focusing on this so much. Um, so once I finished high school, I moved up to Flagstaff, Arizona, to Northern Arizona University, which is at 7,000 feet. So it's actually a pretty snowy campus, which surprises a lot of people because it's in Arizona. You kind of expect desert across the whole state. But it's actually like full 4 seasons, all of that. Um, and I have such a distinct memory as a pre-med major sitting in my Bio 101 class and just realizing I just don't like studying biology. And that it really isn't like studying biology is a fantastic subject, but for me, I just realized I don't think I can do this for my career. And luckily, I listened to my gut and I said, okay, well, I still like science and I really like chemistry. So maybe I just need to explore the different career options that I could look into with a degree in chemistry rather than trying to go the med school route. And that's when I emailed one of the professors at Northern Arizona University who studies inorganic chemistry. Her name is Stephanie Hurst. She's been a professor there for many years now. And she was one of the greatest mentors I've ever had. She was able to help me figure out what I wanted to do as my career and help me grow as a scientist. And I was actually in her research lab for 4 years. So I went to undergrad for 4 years and then I took a gap year. So from sophomore year on, I was working in her lab. And what I was doing in that lab was organometallic synthesis. So you can think of this as basically doing a lot of organic synthesis and then attaching them to metals. So my main project was synthesizing these really bulky phosphorus-based ligands that can attach themselves to metals. Um, and this synthesis was actually shockingly easy. You would really just mix this large, let me see if I can get the laser pointer, maybe not. Uh, Never mind. So I would mix this tropylium compound, which is just a seven-membered carbon ring, with this really common phosphorus compound that has these larger phenyl rings, and it would form into this really nice complex. And after doing that synthesis, we would do another synthesis where we would then form it into what's called a bidentate ligand. So basically, these two big rings can act as a sandwich and they can basically hold on to metals in the center of them. And so the motivation behind this work was potentially to develop these ligands for different medical applications. And so that was what I worked on for quite a number of years. So this involved a lot of organic and inorganic synthesis, including some air-free chemistry, which if any of you guys are chemists or have taken like organic chemistry, it's very fun, but very stressful because keeping air out of a system is pretty challenging. And a lot of different characterization techniques, such as NMR, IR, and X-ray diffraction, so that you can get these cool molecular structures based off of the crystals that you form of the compounds. So I was loving this area of chemistry. I really thought that I was going to stick in organometallic research and probably become a professor, go to grad school, all of that. That was my plan. And of course, because, plans never go according to plan, I went to grad school. So I started at University of California, San Diego, doing similar research. Can't really talk about the specifics too much, but it was a lot of very similar research, doing a lot of synthesis, a lot of air-free chemistry. And in a similar experience to when I realized that biology was just not for me, I realized that synthesis also was just not exactly for me. I can't really put a finger on the exact reason why. The only thing I can say is that going from undergrad research where you have a lot of different other things pulling your focus, and then going to grad school where you're really focused on one project and one single thing, it really changes the game for what you might find interesting or what you might want to stick with in the long term. So I was actually considering dropping out of grad school at this point. I was pretty disheartened. I was like, well, maybe science just isn't for me. Maybe I need to do something else. But I did know that I still loved chemistry. I still found my classes really interesting. And I also wanted a PhD. So I gave myself a little bit of time to think and thought about other areas of research that I might find interesting and kind of thought back to growing up, as a kid, what was I interested in? And I was always fascinated by clouds and the atmosphere. And as fate would have it, UCSD has a huge atmospheric research facility, both at Scripps as well as in the chemistry department. There were a number of professors doing atmospheric research. So I started looking into that as a potential option. And so a lot of the work in this field is focused on aerosols. Now, what are aerosols and why should you care about aerosols? Because I care a lot about aerosols. When you hear that term, you probably think of spray paint or hairspray or cans, the kind of fine mist that's generated. And those are aerosols. But aerosols come from a lot of different sources. The true definition is just particulate matter suspended in a gas. So you can think of like the gross biomaterial that you get out of a burning forest, smokestacks, volcanoes, all sorts of stuff. These are all forming large amounts of aerosols, and aerosols play a huge part in our overall atmospheric radiative budget. So, how much energy from the sun are we absorbing, and how much are we reflecting back? And the other really cool thing about aerosols and why there's so much focus in many atmospheric groups right now on aerosols is because they actually act like mini reactors. So if you are familiar with bulk chemistry, a lot of mechanisms have already been determined and they behave as we expect them to. But when you have such a tiny droplet, you get some really weird interactions that you wouldn't necessarily expect in the bulk. And we end up seeing that in the types of reactions we see, which I will get into later. A couple of these different causes for these weird reactions are solvent evaporation. So if you have, an aerosol, and granted, this is right, this is scaled up crazy. We're talking much smaller than a human hair here. You have all this surface area, so it's easy for solvents to evaporate out. You can also get kind of crust formation on the surface, which affects basically which types of molecules, gases we'll see. You also get physical confinement of the different chemicals. So you're basically just like pushing them all together, and that can also cause weird reactions. And they're also charged and can generate their own electric field, which causes some very weird oxidant chemistry to occur. So, like I said, so I was at UCSD trying to figure out what I wanted to focus on, looked into the atmospheric research groups, and decided to work with Professor Jonathan Slade. I actually met him his first day on campus and said, "Hi, can I be your first PhD student?" And I got lucky that he took my enthusiasm and was like, "Yep, you can come work for me." And so his main focus was on sea spray aerosol. So I showed some examples of like smoke and things like that, but one of the biggest sources of aerosols into our atmosphere is through sea spray. So that just happens because of waves breaking in the ocean. You can imagine, a wave breaks, and you get kind of that spume, for lack of a better word, of a bunch of mist, and that's all sea spray aerosol. And so, because our oceans are massive and there's always wave breaking happening, they play a huge role in our atmosphere. And luckily enough, he was a part of this group called the Center for Aerosol Impacts on Chemistry of the Environment, which was a group that was funded by the National Science Foundation that included a huge number of universities across the US and I think potentially some international ones. I can't quite remember now. All focused on trying to understand the chemistry of sea spray aerosol. And so it was a super collaborative environment. And a lot of the funding went into these massive mesocosm studies. And this picture really doesn't do it justice. But what we would do is we had this tank, a quite literally tank, like an aquarium, but it was the length of a football field. Okay. And it would have a paddle at the front, and we would fill it with seawater, and the paddle would move, and you would get waves. And so we would have probably 20 different schools come in during the summer, and we would all bring our different instruments and, however, if you wanted to measure the gases or the aerosols or, whatever aspect of it, all bring their instrumentation down, and we would all measure off of this one tank so that we could compare our results. And it was a really cool experience, very, very time intensive and at points stressful, but really cool collaborative environment. And so this was my first experience in atmospheric research, but this wasn't quite what I wanted to focus on. I mean, there's to a certain degree, you don't necessarily get to choose what you focus on during grad school because a lot of that has to do with the funding sources that your advisor has. But the project that I was focused on and more excited about was actually looking at plastic and plastic pollution. So this is actually, I included this in my thesis defense. This is the Great Wave off of Kanagawa by Hokusai. I'm sure I pronounced that wrong. I apologize, but very famous painting. And then there was this rendering that came out a couple of years ago that just kind of represents how much plastic waste is in the ocean. And the plastic waste, I don't think, I think everyone is aware of. I don't know that everyone has a true grasp of how terrifying plastic waste can be. So this is just a current, is slightly outdated estimate of how much plastic debris do we have in our oceans. And you can see here that across time, it follows a roughly linear shape, right? Makes sense. We're generating more plastic. There's going to be improper disposal of plastic. It's going to end up in our oceans, right? But the scarier part about plastics is that they don't degrade like normal, like a banana peel, right? It's not going to just dissolve. Instead, they fragment and fragment and fragment into tinier and tinier and tinier particles. So you can see here that in plastic particles, and this is in the trillions that are present in the ocean as of, let's see, this would have been in like 6 years ago, maybe. So it's even worse now. That this is actually an exponential growth in the amount of plastics. We're on a log scale here. Um, and again, the issue is that they just keep breaking down into smaller things. They don't actually dissolve or degrade through any natural processes. And from an atmospheric perspective, once they get to a small enough size, they can become aerosolized just like any other normal aerosol. And they've been found in rain and as far remote as the Arctic, they've been found across the globe. Um, and part of the issue, similar to how I was speaking earlier about aerosols and how you have these weird confinement reactions and just weird chemistry that happens, as these microplastics break down, their volume decreases, but their overall surface area increases dramatically. And that can increase how much chemicals they can leach out. So you can think of plastics as being kind of like a weird kind of crate almost, right? Where you have a bunch of little holes in this lattice work where you can have different chemical compounds that are added to give the plastic its properties. Well, when you have increased surface area, you're going to have all of those little tiny compounds resting in this lattice leaching out from those plastics. So it's not just the physical microplastic that's the issue, it's also the chemicals that it releases into the surroundings. So my work was focused on bisphenol A. You have almost definitely seen bisphenol A when you go to the grocery store and you find a can of food that says it's BPA free. It's used in plastics to harden the plastic, but the bad thing is that it's an endocrine disruptor in the body. So it basically messes with your hormones because your body thinks that it is a hormone, but it's obviously not being generated in a natural way. So your body kind of freaks out. It can also be carcinogenic, so cancer causing. And some work has found that it actually leaches 6 times faster than other plastic additives inside of that lattice work. So we know that plastics that contain BPA are more likely to leach that BPA out into the surrounding water much more quickly. Some studies have found that it can be persistent for up to 35 days in seawater, and BPA itself has also been found in aerosol globally. And so part of my work was with this knowledge that BPA is getting into water and that water is being aerosolized. What is the lifetime? You know, when you go to the beach and you breathe in the salt in the seawater and all of those aerosols, are you being exposed to BPA? And I won't get into too much of the technical details here, but one of the major findings that I worked on is that when you have bisphenol A in non-saltwater systems, so you can imagine like lake water, things like that, the lifetime hovers around 20 days in atmospheric aerosol. But upon the addition of sodium chloride or salt, sea salt, you actually speed up the degradation of BPA by about 3 times. So we see much less retention of BPA in the atmosphere, which can be a good thing. There's a lot, the unfortunate thing is it's kind of just like an onion of problems a little bit because yay, we're breaking down BPA, but it can also break down into more toxic compounds and sometimes into less toxic compounds. So there's still a ton of work to be done in this area. But yeah, so this was my kind of primary project while I was in grad school that really that was my pride and joy while I was working on in grad school. Um, so then when I was approaching the end of my PhD, I was looking for jobs, as many people do, and I didn't really know if I wanted to go to a national lab or if I wanted to go into academics. So I was kind of just applying, maybe not everywhere, but if I saw something that looked interesting, I went ahead and applied to it. And there was a job opening in the analytical department here, and I applied and ended up getting the job. So I've been here for about 2 years now. Um, and while I've been here, in the similar way to grad school, you're kind of up, it's up to your advisors where your funding comes from. But I was still really focused on this issue of microplastics. And so I actually went out and found my own funding through a project or a program called Exploratory Express, which funds projects that are high risk in nature and are for a very short term, so just for a year. And I was awarded it. And so now I'll go ahead and share kind of the idea behind that research. So I already shared that microplastics in the seawater and in the environment are a problem. But now that they're breaking into smaller and smaller pieces, they are now becoming a massive health concern for humans. So microplastics represent up to 13% of the particulate matter or the aerosols that are present in urban environments. A lot of that comes from tire wear, but it can also come from like if you wash polyester clothing, it can come from that. If you cut open a plastic container, you can actually generate microplastics from that. It comes from all sorts of different sources. But the main point here is that it's representing quite a large portion of the aerosols we're exposed to on a daily basis. And there was some work that came out recently that showed that adults are exposed to up to 68,000 microplastic particles by inhalation per day. So this is not in your drinking water. I mean, it is, but this study was just looking at what you're inhaling, what are your lungs exposed to. 68,000 pieces every day that we are being exposed to, which is pretty terrifying, if you ask me. Um, and on top of that, as they continue to break smaller and smaller, they have a tendency to bioaccumulate. So you've probably seen the headlines of like we ingest a credit card's worth of plastic in a year. And I know that some of those studies have come under a certain amount of scrutiny, but at a certain point, it's just a there is no getting around it. As they break smaller, it's easier for them to bioaccumulate. And because microplastics tend to be hydrophobic, they tend to bioaccumulate in fatty areas of the body, including your brain, which is contains a lot of the fat in your body. So I really wanted to focus on microplastics, especially because they can also undergo all of those unique chemistry that we see from aerosols when they're in the atmosphere. So I won't go into all of the details here, but you basically get a bunch of different interactions with gases reacting at the surface or potentially diffusing into the particle and reacting there. The interesting thing about microplastics is that this chemistry is dependent on the type of the polymer. So you can imagine like a piece of tire will behave differently than your water bottle will. So there's a lot of different chemistry that's affected by the type of polymer that you have. The other thing about microplastics is we've already seen that they are effective in the atmosphere to seed clouds and ice particles. In areas where you don't have a lot of ice particles being generated, so you can think about like around the equator, microplastics are actually generating about 40% of those ice particles. So this is playing a huge role in how clouds are being generated in our atmosphere. And they also, while they're in the atmosphere, can absorb pollutants, which increases the potential environmental influence of those pollutants, and basically exposing more people to this stuff. Um, so when I was looking at the research that was currently being done, I saw that we were kind of limited in how we could measure the composition. So IR and Raman spectroscopy could observe bulk chemical changes, but we didn't really have any detailed chemical information about what was going on. On the other hand, we could get more specific chemical speciation from things like pyrolysis GCMS, but that wasn't surface specific, or it Yeah, so it was basically measuring the entire microplastic and not what was happening at the surface. And we know that that's where most of this chemistry is happening. So that's what inspired me to look into this research and apply for this grant because I really thought we need to find a better surface-specific microplastic composition measurement technique. And I thought about some techniques that we have in the lab here at Sandia. And one of those is called matrix-assisted laser desorption ionization mass spectrometry, which is a very long phrase to say that we hit it with a laser and we have this matrix compound that absorbs the energy from that laser and helps generate ions so that we can measure the chemical composition of our material. So typically how that's done is you mix one of these matrices, so picolinic acid and 2,5-dihydroxybenzoic acid are the examples I'm showing here. But there's a bunch of different ones. They just absorb that laser energy really well. So you'll mix that with your analyte and then hit it with that laser and measure it. But I thought, okay, but there's some research showing that if you coat a material with matrix instead of mixing it all together, you can actually get some depth information about the chemical composition. And so thinking, okay, well, can we apply this coating to microplastics and actually get some depth resolved composition of microplastic? And the answer is yes. So as we apply thicker and thicker and thicker matrix coatings to these microplastics, you're going to sample less and less of the plastic over time. You can think of it like eating a piece of cake, right? If you have cake that has thicker and thicker and thicker frosting and you use your fork to, take a piece of the cake, you're going to get less and less cake as that amount of frosting increases further and further. We actually see a pretty strong dependence on this coating thickness and the amount of polymer that we sampled. So this was pretty successful and really cool. It's still in the early phases, but we think that there are a lot of different applications that this can have at the labs and in science as a whole. And this also gave me the really cool opportunity to present at the National Lab Slam this past year. So in April of this year, I presented my research in a 3-minute slam format, which is kind of like an elevator pitch on Capitol Hill. I was competing with postdocs and early career members from the other 17 different DOE national labs. And also during this experience, I got to meet with other senators and representatives. And it was just a really amazing experience that I don't think I would have had the opportunity to do if I hadn't been at Sandia. And I also did win my category, which I'm still very happy about. But all my competitors were amazing. Um, and I got to share this research, which is really the whole goal of all of this, is that we get to spread our research and share it and hopefully have more people getting interested in it and wanting to fund it in theory. So that was my first project or first big project, I'll say, working at Sandia. And then I started working on PFAS. So you have probably heard about PFAS, I think. Although I will admit, before I got to Sandia, I didn't focus on PFAS a lot, at least when I was thinking about different concerns in the environment. And I think it's maybe because it's been around for so long that maybe some of the excitement around it has died a little bit. But part of the issue, so PFAS are just these long chain carbon molecules with a bunch of fluorines attached. And this gives them some really great properties for like waterproofing. Teflon materials like pans is made of PFAS, things like that. But the issue is, okay, if they don't break down in those materials, they also don't break down in your body. So a couple facts about PFAS. They're present in over 45% of drinking water sources in the US. So roughly half of the US is being exposed to PFAS and consuming them on a daily basis. About 50% or more of the airborne PFAS are present in the aerosol phase. So that means that they're in some of those droplets rather than in the gas. And so when we inhale these aerosols, they can stick around in our lungs and increase our exposure. And like I was saying, they don't break down well, and they also have a lot of negative health impacts. The majority of PFAS are both carcinogenic, so cancer causing, and teratogenic, so basically bad for fetuses. And there's probably a lot more health issues that PFAS are causing that we don't even know about yet. Part of the reason why they are so strong is because of that carbon fluorine bond. It is, I believe, the strongest chemical bond that you can have. And so it just doesn't want to break down, which is not great. And that makes them so environmentally ubiquitous. The other issue with PFAS is with all of these efforts into how do we get rid of PFAS? How do we decrease the concentration of these long chain PFAS? What ends up happening is you actually just get smaller and smaller and smaller PFAS. In a lot of cases, you aren't actually degrading it into like just fluorine or into something that wouldn't be hazardous overall. And so that's a big challenge in this area is we want to get all of the fluoride off of it because that's what's really causing the problem and what's making it so persistent. So I've talked earlier about how we can get such weird chemistry at the surface of aerosols. There's been some recent research that's shown that in these aerosol droplets, even with just exposure to nitrogen, so no oxidants present, nothing that should be reacting, we can actually see degradation of PFAS at that interface. Um, and so there's a lot of work being done in this area, but one of the focuses at Sandia is, helping people and helping the community and the US at large. And the issue of pollution in our water sources is actually a major national security issue. And so, what's something that we can investigate that would have a very quick turnaround time to actually being implemented? Because a lot of PFAS breakdown methods are using like this super hot plasma or these weird catalysts and stuff, which is all great research. I'm not trying to say that it isn't, but that would be very hard to turn around and actually put in our water supplies or add to treatments. But ozone or ozonolysis is already a widely used water treatment process. Um, and it hasn't been shown to be effective for PFAS previously, but we thought, well, let's see if we can spray these droplets and see if ozone breaks it down, because that would be really easy to implement. And so we ended up building this microdroplet sprayer, which is really just a very thin tube with a slightly larger tube around it, where we feed in PFAS through the top in a liquid, and then this nitrogen will basically surround it and basically make the droplet burst into a bunch of aerosols. So once we have that spray generated, this is obviously open to room, but we have this encased because you really shouldn't be breathing in a bunch of ozone. But we'll expose those droplets to high purity oxygen and ozone, and we look to see how readily we're breaking it down. And our initial results are pretty exciting. So we found that when you have a lower PFOA starting concentration, you actually have a much higher efficiency um, for how much of the PFOA you're degrading, which maybe sounds slightly obvious because yes, if you have less concentration, then there's going to be less that you're able to degrade, I suppose. But the important thing here is that if we're able to break down more of it at low concentrations, that would actually be more effective for most of our water sources because those are present at very low concentrations to begin with. So we wouldn't have to concentrate that water first in order for it to be effective. The other interesting thing is that when we compare the types of degradation products between nitrogen exposed microdroplets and nitrogen plus oxygen plus ozone droplets, we see a lot more of the longer chain compounds present, shown here in the black bars. Um, those are the longer chain PFAS. And when we add in the ozone, we get the growth of a bunch of smaller PFAS. And I know that I said earlier that that wasn't necessarily a good thing, but you have to start somewhere and you do have to initiate the breakdown before you can begin to fully defluorinate them. So this is exciting. And right now we're working on basically extending this ozonation process so that we can actually get full mineralization of the fluoride. So that's kind of a summary of what I've worked on in the past and what I'm working on here at Sandia. Now I want to talk a little bit about what we do here at Sandia. So we are a federally funded research and development center. So we work primarily on different national security challenges. So I have a bunch of phrases that are present on the website, but I would say that a majority of the work here is done by a lot of fantastic engineers to protect the public and basically make our weapon systems and things like that safer. The other big portion of work that we do is a lot of fundamental research that is um, applicable to the community at large. So if you think about PFAS in our water, that's a huge national security challenge. Microplastics, being breathing those in, that's a public health issue. A lot of things that you might look at on the surface and say, well, that's just environmental research. Why aren't you doing that at a university? It actually does have massive implications for national security and just what we do as a whole. Um, so just these are just my perspectives. For those of you who are thinking about maybe I'd be interested in a national lab, there's a variety of pros and cons, right? As any job would have. So the pros here, you have a huge variety of projects to work on. So I counted before this presentation. In the 2 years I've been here, I have worked on 17 projects. Some of them very short term, some of them longer term, but we work on a whole variety of things. And because we have so much funding, we have access to a lot of different instruments and techniques that you might have access to at a university, but you probably wouldn't have access to all of them at once. And this lends itself to a really highly collaborative environment, which is just an amazing way to work with a bunch of other scientists on problems that we all care about. It also has a really strong culture of safety. So when I went from grad school to Sandia, a lot of the things I did in grad school would not have flown working here at Sandia, um, because there's just a lot more focus on making sure that the workers here stay healthy and that they're not risking their lives when they come here to work. Some of the cons, as you can imagine, we get a lot of funding changes with fluctuations in government, but that's most science, unfortunately. There are very few constant sources of funding that don't change over the cycling within the government. The high number of projects also means it's a pretty steep learning curve. So it can be challenging in the beginning, especially, but it's definitely worth it in the long run, in my opinion. The other thing that I definitely didn't expect is that the funding cutoffs are much sharper than in academics. So in academics, a lot of times you'll have a professor that does XYZ type of research, and then their research funding kind of continues for many years, for their entire tenure. Here, if you don't have a project immediately lined up to continue the work, you're not continuing the work unless you're doing that in your free time. So it means that you have to be really on top of how productive you're being. And when something isn't working, you need to kind of cut it and move on to the next idea that you have. There's also lots of red tape, but I don't think that's too surprising to anyone here. Um, so the other thing I want to talk about is there are tons of opportunities for students. And when I say students, I mean undergrads and graduate students. Um, I've listed a couple of them here, or I haven't listed them. Natasha listed them and sent them to me. But this is just kind of a sampling. So there's like the technical internships to advance national security internship, future of research for secure and energy and earth systems, student intern group for microelectronics advancement, and then the URA Sandia Graduate Student Summer Fellowship. But this is just a selection, right? There's a lot of other opportunities. So if you're interested, I would very much encourage you to go to Sandia's website and take a look at what sort of positions are available. And even if you can't apply right now, if it's not in the application cycle, come back and check later because these opportunities are always opening up. I have two last pieces of advice that I would like to give to you guys before I end my presentation. The first is don't be afraid to switch fields, especially early on when you're, in undergrad or grad school. If you're doing research and you start to find that you're just not really interested in it anymore, don't give up immediately. But if you're like, this really isn't for me, don't be afraid to switch. It happens a lot more than people talk about, and there's nothing wrong with it. Like some people thought I was crazy when I told them I'm going from organometallic research to atmospheric research, but it just bettered my career, honestly. And now I'm in a field that I really love instead of being stuck in something that I wouldn't have loved as much. My other piece of advice is to take opportunities to the best of your ability as they come to you. So even if you don't really see how it's going to impact your career, it might be worth just taking it anyway. So like the National Lab Slam, that started as a slam competition here at Sandia where it was just Sandia postdocs and competing against each other. And I didn't even place in that one. But then they ended up calling people back and saying, hey, we thought you did a great job. Can you compete at this level? And it just kind of kept growing. And if I hadn't been open-minded to presenting, I wouldn't have gone after the slam. I would have said, it's just a 3-minute research talk. What is it actually going to accomplish? Stuff like that can actually make or break your career in a lot of ways. So take those opportunities when you can. Lastly, I would like to thank my research advisors, Ryan Davis and Jessica Kustis, my fellow postdocs, lab members, and then Natasha and Cindy for helping organize this seminar series. So thank you so much, and I'd be happy to take any questions.
Fantastic. Thank you so much, Samantha. This was a great presentation. I encourage our attendees to use the Q&A feature found at the bottom of your screen to go ahead and ask questions, and I will read them out loud. So to kick things off, you just talked about the slam competition, and I was wondering if you can talk about maybe what are some other professional development opportunities that you've come across at Sandia that either you've participated in or just seen in regards to like doing extracurriculars, because traditionally at a lot of universities you can join school clubs, right, and do all of these extracurricular things. Is that culture like is there that can that culture be found at like Sandia at the National Lab?
Yeah, so it absolutely can be found here. And honestly, I would say that some of those kind of community events are even stronger here at Sandia than they were in grad school. There's a lot of people here that are passionate about jazz music or hiking. Like there's a hiking club and all sorts of different kind of opportunities to meet people like that. There's also the postdoc community here is really strong. You can get involved by joining the um, postdoc leadership committee, I believe is what it's called. But basically, just organizing events for postdocs to expand their career horizons and things like that. So that those are just a couple of examples. We constantly have events going on, like different workshops that are exclusive to Sandians. So you can meet people from across the labs who you wouldn't normally meet on a day-to-day basis, and just tons of different opportunities like that. So it's honestly it's a lot broader than I would have expected. I kind of thought you come here and you work in your lab and you're kind of, you know, sectioned into your spot and you don't meet a lot of other people, but there are actually tons of activities here. And there's also a really big focus on giving back to the community. So there's always postings for helping out with like school science fair judging or different volunteer opportunities as well.
Awesome. Thank you for that. We have a question from an attendee in the Q&A. Um, this person is interested or is wondering whether it's possible for graduate students to discuss potential research ideas with scientists at national labs and potentially develop collaborative proposals or future postdoctoral opportunities. And they were wondering if you have any advice or guidance on how to go about doing something like this and building those research collaborations with national labs.
Absolutely. So there's a huge focus on kind of starting those relationships early on so that they can become a postdoc opportunity. I will say that we do have a large number of graduate student interns. So basically, they're doing their primary PhD or master's thesis somewhere else, but they do the research here. So that's one way to get involved. I would encourage you, if you have a research mentor at this time, to maybe talk to them about some of those opportunities. But you can also just start reaching out to people. I honestly, it makes my day when someone reaches out to me out like in random and they just start asking me questions about like, is there an opportunity for this here? You know, are you doing any research in this area? There are also formal opportunities that I want to mention, the Ruby Fellowship, as well as of course, now I can't remember the name, the Truman Fellowship. Those are two big fellowship applications where you submit an idea to Sandia. This is for graduate students who want to be postdocs. So you submit your idea, and then folks at Sandia will actually help you meet up with researchers in your field at Sandia, and you form a collaborative proposal that then goes on to the next round and then gets selected by a bunch of committee members. So that's another formal way to do that type of research.
Awesome. Another question from the audience about the 17 projects that you've worked on, how much of that was driven by your own choice and interests versus being assigned based on lab priorities?
It's a great question. I would say I think it probably like roughly 50-50. I can't really put a number on it because there is a lot of work that comes in and it's kind of like, well, someone needs to do it, right? But because we have other coworkers, like there's a pretty good amount of flow, I would say, in if you're not interested in it, someone else in the group will be interested and they'll want to work on it. But most, if not all of the projects I've been really excited about, even if they weren't something that I would have picked initially.
Another question, are international students allowed to apply for postdoc positions at Sandia? And if so, when do those applications or when is the best time to apply?
So this is from my understanding, so I will put an asterisk on this, but I don't think there are any limitations on having foreign students apply for postdocs. So postdoc positions come up through the Sandia Careers portal. So if you just go to Sandia Careers and Postdoc Opportunities, that's where you can find most of the opportunities for any postdocs who are interested. There are some restrictions on foreign students working here. Certain areas aren't allowed, and certain areas of research aren't allowed. But I work with a number of different foreign students who are doing postdocs here, so it's really not probably not the as much of a barrier as you might think that it is.
Thanks for that. In terms of the microplastics research that you shared with us, can you help us make the connection between why Sandia, a national lab that focuses on national security and defense, would be interested in the microplastics, the aerosol, the environmental concerns?
Yeah, absolutely. So, one of the aspects for environmental research at Sandia is comes down to um, basically how much of a problem would it cause for the US if this became a bigger issue? So, for example, like with the PFAS pollution, um, most of the PFAS pollution is actually centered around military bases because that's where a lot of the initial testing was done. And so there's a kind of enhanced interest from a national security perspective that, our soldiers are not generating health problems from the water that they're drinking. And it comes down to where our water sources come from. Do we need to start looking, internationally for clean water? That's not good, right? That introduces another security issue. So it stems a lot from that type of issue. A lot of times it's just how you frame it. But then the other side of things for the microplastics research is that what I was developing was based on an environmental problem, but it's technically just a technique. So I've been able to apply for a lot of other different funding sources that just use this technique on another system. And that's another way to get funding here is, okay, here's the problem I want to focus on. Here's how I want to do it though. And if this technique is new, then that can be applied to a bunch of other like defense applications.
Thanks for that. You talked about the pros and cons of working at a national lab. Could you talk about kind of the work culture that you've experienced? Do you work with a large team? Is it just you doing this research with an advisor? Like, what do the team sizes look like? And maybe are you and what does your day-to-day look like?
Yeah. So I'd say in general, our teams, I don't know, it kind of varies. So sometimes we get what's called customer work where someone will come up to us and say, hey, I need you to measure this aspect of this piece of material we have. And so for those projects, that tends to be kind of small teams. It's typically the customer who's asking us these questions, and then maybe myself and a technologist doing those measurements and then reporting back to the customer. So those are kind of the smaller sizes. For other projects where it's like are more research focused, those tend to be a bit bigger, maybe 4 to 5. I typically work with another postdoc on those projects, typically on different focuses though. So, like someone I work with very frequently, he's more of a materials science person. So he'll do like PFAS absorption studies, whereas I'm doing the aerosol side of things. Um, and so the problems that I have in my research, like scientific problems that I run into, I'm typically the only person working on them, but I can go to any of my lab members and talk to them about it, and they'll have a unique perspective about those issues. Lots of times I'll talk to our basically inorganics person about issues, and he has some really interesting ideas all of the time about how we can solve these problems. As far as my day to day, I typically work from, I think it's like 8 to 4 most days. Some days our mass spec will break and I'm stuck here until 7 fixing it, but that's of my own accord. That is not forced on me by my advisors or anything like that. Um, a lot of writing, lots and lots of writing between proposals and papers and reports. Um, it's basically just that and experiments in the lab that I'm really focused on. But Sandia has a pretty big emphasis on work-life balance, and I've definitely like it's not postdocs aren't expected to do some crazy heroic amount of work all of the time like you might sometimes see in academic labs.
Thank you for that. For students who are undergrads thinking about like summer internships and summer research, what would you say would be like a realistic research question or a goal for an undergrad that could answer in that, 10 to 12 week span, that could potentially contribute to your work?
Like to my work specifically, or just kind of like how to formulate that kind of question?
Yeah, like to your work specifically. If you were to have an undergrad to do an internship for your work, I guess what would be like realistic research goals to think about for the summer? Because a lot of the times in these internships, 10 weeks, 12 weeks fly by, and it's like, how do you get a whole research project done when, sometimes in academia, a PhD can take multiple years. So,
That's a really good question, and I think partially to answer that question is just a skill you develop over time. You start to see how bigger questions need to be kind of simplified. And I think that was advice that I got very early on from one of the staff members in this group was uh, I had this idea for studying microplastics in wildfire situations. And she was like, well, that's a big question. That's like so many different variables. Can you even measure the composition of microplastics? And that's where that started. So I would consider the size of your system and just kind of think functionally about the number of variables that you want to test. So, for example, if you say that I want to test 5 different PFAS compounds in with gas mixtures of nitrogen, nitrogen and oxygen, and nitrogen, oxygen, and ozone. Okay, so that's 5 times 3. So now you have 13 separate systems, or sorry, 15 separate systems that needs to be studied. You expand that to how are you going to do the analysis? Okay, I need to do mass spec and I need to do ion chromatography. So now you have 30 samples from those batches, and you can see how these questions keep expanding and they just exponentially grow. So I would say whatever your idea is, just like chop it in half. Like cut the number of PFAS you would want to focus on, or chemical compounds or absorbents, things like that. Cut it in half. Basically, just lower the scale because it's always better to lower the scale and have a really good answer at the end of those 10 to 12 weeks that you can actually publish on than doing a bunch of experiments but not being able to do all of them. And then you still have some questions left unanswered. And that'll always happen. You can't completely avoid that, but just cut the scope by a lot, more than you think.
absolutely. Well, I want to give you the last couple of minutes if there's anything that you want to say, final remarks to our audience. The floor is yours.
Sure. I'd just like to say thank you all for attending. I really appreciate having just seeing the interest in this work. And I really thank you for your attention. And I also want to thank Natasha again for hosting today and taking all the questions and everything like that.
Fantastic. Well, thank you again, Samantha, for your presentation. I know a lot of people enjoyed it, and I definitely learned a lot. And thank you, everyone, for attending. At the conclusion of this webinar, a Zoom tab should open up for a quick 3-question survey, and we would appreciate your input. And then our next seminar will be on Tuesday, June 23rd at 1:30 p.m. Eastern Time with Idaho National Laboratory. So stay tuned for an announcement on that. And with that, thanks everyone for attending, and we wish you a good rest of the day. And thanks again, Samantha.
Absolutely. Thank you again, everyone. Bye.